Welcome back to Ubad's lab, and today I'm going to be explaining how to integrate acceleration with an object that's experiencing drag. Alright, so this is the object that we're working with in this problem. So the object is traveling in the positive x direction, and it's on a frictionless plane. And there's actually no force acting on it this way, but it's still traveling that way, which will throw people off. But this is a common example of Newton's first law of inertia. So an object that's in motion will stay in motion. So the motion in this direction is given by v naught. It starts at position x is equal to 0. And then there's another force, which is negative kv, and that's the force of drag. And you can see that it's a negative kv, which shows that the drag is dependent on the velocity, because the higher the speed, the higher the velocity of an object, the more drag it experiences. So the acceleration will actually be decreasing in this problem. That's something that's crucial to understand before we dive into it. And our goal for this problem is to integrate using, we just know these three things, and we can integrate a equation for position versus time. First, we're gonna have to take an equation for acceleration versus time, integrate it, and then find the equation for time with velocity with respect to time, and then we can integrate that and find an equation for position versus time. So let's get into it. First, we're gonna have to sum the forces to figure out acceleration versus time. So the summation of forces is equal to ma. And the mass, we're just going to be working in terms of variables, and the mass of this object is just going to be m. And the sum of the forces, the only force that's acting on this object is negative kv. And so as I previously stated, it's just traveling by itself, since it's in this problem, it's just starting in motion, so there's no force that's keeping it in motion. It's the Newton's first law, which is equal to m times a, and we can just solve for a by dividing both sides by m. So we know a is equal to negative k over mv. Alright, so we just solved for acceleration. Now we want to integrate this to solve for our velocity. So what we can do is turn this into a differential equation. So if a is equal to negative k over mv, we can take this and turn a into dv over dt, because that's what acceleration is. It's the instantaneous change in velocity with respect to time, is equal to negative k over mv. Alright, and now we can multiply by dt, so dv is equal to negative k over m dt. Alright, and I forgot the v over here. There we go. Alright, and now we can multiply both sides by v. Okay, so we have dv is equal to negative kv over m dt, and then we can multiply. We have a v over here, which I forgot to put, and now we can multiply both sides by v to turn this into dv over v is equal to negative k over m dt. All right, and now that we have this, there's we can turn dv over v into now we need to integrate, right? And now we can turn dv over v into the ln of v. And that's just a law of integration that you need to know from calculus, basically. So you need to know that the integral of 1 over x is equal to ln of x. And basically, if you know your derivative rules of transcendentals, you'll basically know that because the derivative of 1 over the derivative of ln of x is just 1 over x times the derivative of x, which is 1. So we have ln of v is equal to, oh yeah, so always set, because we're not working with, we're working with definite integrals. We're not working with indefinite integrals, so we have to set our limits. So this is from v naught to v, because we know that we're starting at a certain speed. And for time, we're going from starting at 0 seconds to t, because we don't know how many seconds. So I just set the limits right there. And ln of v from v naught to v, because we always have to give our limits, evaluated from v naught to v, is equal to, what's the derivative of negative k over m? Well, so whenever there's a constant, we can always throw that constant into the front, and then the derivative of dt is just t. I mean, the integral of dt is just t, because we're adding 1 to the exponent and then dividing by that new number, and that will become 1. So negative k over m t, a value from 0 to t. And then this will equal, to evaluate this, we can do ln of v minus ln of v naught, because we're finding the difference between these two integrals to find the area between them, which is equal to, if we plug into 0 into this, then we'll just get 0. So we can just not show that step and just plug in t, so we get negative k over mt. That's an m, by the way. Okay. And now this is just a transcendental rule of ln, that ln v minus ln v is equal to ln v over v naught, negative k over mt. All right. And now what we can do is we can use another transcendental rule, that if we throw in these as exponents and put in them to the e, so e, and that's the exponent, and the e, that's the exponent, then we can, it's just a rule of ln. So v is equal to v naught. So e to the ln, and whatever's in the parentheses or the absolute value, that's what it's equal to. So v is equal to v naught. It's equal to e to negative k m over t. And that's just the way we were able to isolate the v's. Okay, and now we can multiply both sides by v naught to isolate the v. V naught e to negative k over m t. Okay, nice. We just got this our equation for velocity versus time for this object. And now we can get into integrating the velocity to find the position versus time. Okay, so I'm just going to rewrite this over here. We have v is equal to v naught e to negative k over mt. All right, so what's our first step again? We have to turn this into a differential equation. So we can turn this into dx over dt, so to v naught e negative k mt. All right, so it is position, the change in position with respect to time. That's what velocity is. Okay, and now we can start integrating this to turn it into position versus time. So we can throw this dt onto the other side. So dx is equal to v naught e negative k m t dt. And I just multiply both sides by dt. And now we can integrate this. And we know it starts at position 0. And it goes to x. And then we integrate this. We know for time it goes from 0 to t. Okay. All right. And the integral of dx is just x a value from 0 to x, but we'll get rid of that soon because plugging in 0 into that will just give us 0. So it'll be x minus 0, which is equal to the integral of v naught e to the negative kmt. Okay, so there is some u substitution involved in this because we have this. Okay, so first of all, we have this v naught. It's a constant, okay? We can throw that into the front. So whatever we get, it's gonna be v naught multiplied by that. But we have this e to the negative kmt. We know the integral of e to t is just equal to e to the t. Okay, but now we have this constant that we're working with here, negative km in there. And a quick way to do this is to multiply by the reciprocal of the derivative of the exponent. Okay, so basically we have negative kmt in the exponent. The derivative of negative kmt is negative km, right? Because we're just subtracting 1 from the exponent there. So we have negative km, all right? And the reciprocal of negative km is negative m over k, and we can multiply by that. So we have v naught, let's throw a negative into the front, m over k, times e to the negative k mt. All right, and the dt is gone, all right, and this will be evaluated from 0 to t, and it's important here because the 0 will not just turn into a 0, because if you throw 0 into an exponent, it will turn into 1. Okay, x is equal to, let's plug in t into this. We get, plugging in t just gives us the same thing, so negative v naught m over k e negative k over mt minus, which will just be plus because we have a negative there, so plus v naught m over k, and then e to the negative km times 0 turns into e to the 0, which is 1. So 1 times v naught times mk, so just that. All right, and let's we can simplify this a little bit. We get x is equal to, we can factor out a v naught mk, and over here we get 1 for this one. I just like the 1 in the front, so I'm throwing a 1 into this one, minus e to the negative k mt. Yeah, all right. That is our equation for position versus time for this object right here. And the integration does get a little complicated at times, but this is definitely something useful to work through for understanding how drag affects this object's change in position. It's a change in velocity. And yeah, that's basically how you integrate your acceleration to get your position equation. Don't forget to subscribe and hit the notification bell if you enjoyed the video. Also, I'm going to be posting a new lab tour video once I hit 400 subscribers. So don't forget to subscribe. Anyways, thanks for watching. I'll see you guys next time.